Hi guys, today we are working on the characteristics of populations. A population is a group of organisms of the same species that live in the same area. Population density is the number of individuals per unit of area. So how many birds live in Leadwood? So I gave you the species, I gave you the number, and I gave you a specific area. If a population has abundant space and food and is protected from predators and disease, the population will grow exponentially. Well, you might be asking, Ferris, what does grow exponentially mean? Well, it means that the population will double, then the population will double, and then the population will double. So it occurs when individuals of populations reproduce at a constant rate. All right, and we're going to draw a little graph over here. See graph of bacteria growth. All right, this is going to be a J-shaped graph. So, just going to sketch a rough graph in here. Okay, so we have time on our x-axis, population over here on the y-axis, and our title is growth of bacteria. So the population is going to double, 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 over and over again until it resembles a J. So J-shaped curve. Moving on to logistic growth. This is when resources become less available and the population growth levels off, it slows down. So logistic growth, as resources become less available, the population growth rate slows or stops. So when we graph this, it's going to be an S-shaped curve. So once again, we're going to sketch this in over here. We have time, we have population, once again, growth of bacteria. So we have our exponential growth, but as it reaches its carrying capacity, it levels out. Our carrying capacity, I'm going to sketch it in red, is going to be this line right here. Okay, it shows up as gray on the screen. I don't know why, but that dotted line is our carrying capacity. That is the maximum number of organisms that a species can support in an environment. So that is the maximum number of bacteria that can live here due to the biotic and abiotic factors. Okay, so let's move on to our second page. We're going to define carrying capacity and then list some density-dependent and density-independent limiting factors. So, carrying capacity. We have talked about this a lot lately, but let's define it one more time. It is the number of organisms of one species that can be supported in an environment. So these density-dependent and density-independent factors contribute to the carrying capacity. They are what help determine it. So let's label what they are, and then we'll go into some detail. So density-dependent limiting factor. These are factors related to the density of the population. Density-independent factors are the exact opposite. Okay, they are factors or effects, factors that affect the population no matter what the size is. No matter the size of population. So let's list some examples. So let's start with density-dependent factors over here on the left. The first one, competition. Competition. Organisms compete for food. They compete for water, space, sunlight, and other essentials. Other things that they need to survive. Okay, so competition, that is a density-dependent factor. The more organisms there are, the more competition there's going to be. Our next factor, predation. Predation. Population control. Caused by predator-prey relationships. So if I increase the number of moths in my area, my number of bats is going to increase because there's more food. The bats are eating more, they're reproducing more, so they increase in numbers, the bats do. So as the bats increase in number, they're going to eat more of the moths, and then the population of the moth is going to go down. Okay, we're going to do some worksheets to show how this happens over time. Our next density-dependent limiting factor is parasitism and disease. So these rob organisms of nourishment. Okay, and these are density dependent because if you have a very large population crammed into a very, very small space, they're going to be coming into contact with each other. As they are coming into contact with each other, they're going to be transferring these disease, these parasites. Think about ticks. Okay, if I have one dog that has ticks on it and he is all alone, he doesn't have anybody to spread those ticks to. But if I have one dog that has a tick and I put him in a dog pen with 15 other dogs, those ticks are going to start to spread. As they spread, they are going to get more food, they're going to get more nourishment, and they're going to reproduce. So the tick population would then go up. The same idea with disease. If I have a person that has a disease and he doesn't come into contact with anybody else, he's not going to spread that disease. But if I throw him into a crowded shopping center and tell him that he has to hug everybody that he sees, he's going to pass that disease on. Okay, so those are density dependent factors. Let's move on to density independent factors. These might be unusual weather patterns. Unusual weather like drought or floods. Any kind of weird thing happening with the weather. It could be seasonal cycles. Okay, so winter fades into spring, which fades into summer, which fades into fall, and as those seasons change, our populations are going to change. Our next one, natural disasters. Like a volcanic eruption, a forest fire, a flood, an avalanche, any kind of natural disaster. It's going to affect every organism in that area. It's not going to matter how many of them there are, but every single one of them is going to be affected. And then lastly, human activities. An example of this would be clear-cutting a forest, or damming up a river, so human activities, it's going to affect every single organism there, regardless of how many there are. Okay, so those are your notes for today. If you have any questions, feel free to shoot me an email or ask me before class tomorrow.